Okay, so today we'll be discussing the concept of parallel lines crossed by a transversal. So here we can see clearly that these two lines are parallel to each other, and we can mark these A, B, say that A is parallel to B. And we can see that it's crossed by a transversal, C. So now on the ACT, you might not come across a specific figure looking exactly like this, but you're going to come across variations of parallel lines and transversals crossing through them. So it's really important to understand your concepts of congruency since that's often tested on the ACT. So first let's discuss our alternate exterior angles. Our alternate exterior angles are 1, 8, 2, and 7. And it's really important to keep in mind that 1 and 8 are congruent and 2 and 7 are congruent. And these are just kind of rules you're going to have to memorize. If you've taken geometry, you've probably already been familiar with them, so it shouldn't be too hard. But yeah, so up top, we could just simply write here that 1 equals 8 and 2 equals 7. That way we could label that these two are both congruent. Moving on, we can move on to our alternate interior angles. So our alternate interior angles in this case are 3, 6, 4, and 5. So it's really important to keep in mind that in this case, 3 and 6 are both equal to each other or congruent. So we could write down here 3 equals 6. And it's really important to also keep in mind that 4 equals 5. So we could just simply write 4 equals 5. Now again, at first this might seem like a lot to memorize, but it's just one of those things you're going to have to keep in mind as you're taking the ACT. Moving on, we can move on to angles 2 and 6, and we could also move on to angles 1 and 5. These are corresponding angles, and it's really important to keep in mind that angles 1 and 5 are congruent, and angles 2 and 6 are congruent. So we could also write that over here, 1 equals 5, 2 equals 6. Moving on, we could keep in mind that 4 and 8 and 3 and 7 are also congruent due to the similar concept of corresponding angles. So 4, 8, 3, 7. We can write those down. So 4 equals 8 and 3 equals 7. All right, so this is our basic fundamental concepts of angles relating to alternate exterior, alternate interior, and corresponding angles. Now we can move on to a very similar concept using vertical angles. So vertical angles are essentially just angles that are opposite of each other. So for example, 1 and 4, 2 and 3, 5 and 8, 7 and 6. These are all equal to each other because you could just tell visually that 1 is opposite to 4, 2 is opposite to 3, 5 is opposite to 8, 7 is opposite to 6. Now moving on, we could work onto angles that are equivalent to 180 degrees. So first off, we can see our straight line angles. So we could see here, for example, 1 and 2 we know will equal 180 because they're on a straight line right here. 3 and 4 added together will equal 180. So we could probably write that down. 1 plus 2 equals 180. 3 plus 4 equals 180. And you can kind of get the idea. 5 and 6 would obviously equal 180. 7 and 8 would also equal 180 for the same concept. Now we could go into our interior angles and we could see that 4 and 6 right here, 4 and 6, are also going to equal 180. This is going to be kind of a concept you're just going to have to memorize, unfortunately, but that's just how it ended up working out. Same with 3 and 5. 3 and 5 also equal 180 degrees. So with these concepts, you can kind of use on the ACT since the concept of parallel lines being crossed with the transversal is often tested, whether it's tested for congruency or if it's tested to find angle measures, etc. Now, in order to ensure that we understand the concepts of congruencies and summation regarding parallel lines being crossed by a transversal, we can solve out an example like this. So let's say we're given that this angle right here is equivalent to 40 degrees. Would we be able to solve out what every single other angle equals to? So let's start off with this angle right here. So since that we know that angles on a straight line must equal 180 degrees, we could simply do 180 minus 40 equals 140. And so here we could see that, okay, this angle equals 140. Now, due to our law of vertical angles, where we see that angles opposite to each other also have to equal the same angle. For example, this must equal this because of our vertical angle theorem. We can say, okay, this equals 140. And again, we can implement the vertical angle idea right here and right here to say that, okay, this angle must equal 40 degrees, right? Now we can move on to our corresponding angles. So we could see right here that this angle is 140. So that means that this angle must also be 140 due to our idea of corresponding angles. So we could state down here, okay, this equals 140. Similarly, we could use the same idea that, okay, this angle equals 40. This angle must also equal 40. And we can almost check our work as well because we know our laws of summation. We know that lines on a straight angle, our angles on a straight line, must equal 180 degrees. And we see that that checks out perfectly here with 140 and 40. Now moving on, it's pretty simple from here. We could see that our vertical angle theorem works out just perfectly for right here. So we can see that, okay, this is 140 simply because that it's opposite to this angle. And we can also see with our laws of our laws of corresponding angles, we can see that 140 and 140 right here as well. And finally, to cap it off, we can see with our vertical angles and our corresponding angles that this must be 40 degrees. And it all checks out because 140 plus 40 equals 180. So little examples like that is how we could see as how we can practice to make sure that we really have these ideas memorized. Because on test day, even though we're not going to have a diagram exactly like this, these concepts are going to be tested at least I'd say once per ACT test. And it's going to be a variation of these sort of concepts and diagram related to vertical lines and transversals. But it's really important to keep in mind that these concepts only worked if A is parallel to B, or if we know that these two lines are parallel, or if any of the lines being tested are parallel. All right, thank you so much. That's the first concept that we'll be going over today for our ACT math content review. Okay, now let's move on to a more complicated example where we see, obviously we have our parallel lines A and B, but we also see that it's crossed by two transversals this time, C and D. Now, given that this angle is equivalent to 40 degrees and this angle is equivalent to 30 degrees, would we be able to find out the value of all the other angles? Now, let's begin. So let's start down here with this 40-degree angle. So due to the law that we had discussed earlier, where two consecutive interior angles are equivalent to 180, meaning that this angle right here and the 40-degree angle must equal to 180, doing some subtraction, we can realize that 180 minus 40 equals 140. So this angle right here must equal 140. So we could write that down right here. So this angle equals 140 degrees. Okay, now we can move on to our ideas of the vertical angle theorem, which basically states that angles opposite each other must be congruent or equal. So we see that this is 40 degrees, meaning that this angle must be 40 degrees since this is opposite to this angle right here. So we can write down 40 degrees right here. Now, another idea that we have is that angles on a straight line must be equal to 180 degrees. So we see right here with 40 degrees that this angle here must equal 140 degrees because 140 plus 40 equals 180, fulfilling the rule that angles on a vertical line must equal 180. So we could write that down right here, 140 degrees. And we could see that right here, similar concept with the vertical angles, we could see that these two must be equal, but we could also see that 40 plus 140 must equal 180. So we could write down that 140 over here. Great. Now we can move on to this angle up here, 30 degrees. So first off, we can clearly see our vertical angle theorem being put to use, that 30 opposite to this angle must also be 30, because of the vertical angle theorem saying that angles opposite each other must be equivalent. Now we could also use the idea of how angles on a straight line must equal 180 degrees, meaning that even though this line is not horizontally straight, this line is still technically a straight line right here. Let's see, line C right here. This line right here is technically a straight line, and so we can see that this must equal 150 degrees, because two angles on a straight line must equal 180 degrees. So we could write down, let's see, we could write down 150 right here. And then, of course, with our vertical angle theorem, we could see that this equals 150 degrees right there as well. This angle right here. Now, moving on, we could see that this angle right here, this angle of 140 degrees, using the vertical angle concept, we could see that this angle right here must also equal 140 degrees. We could put down a 140 right there. And then we could also use our idea of straight lines equal 180, 140 plus 40 down here. That equals 180 degrees. Now, moving on, we can use this idea of vertical angles. We can see that this angle equals 40, meaning this angle must also equal 40. So we could write down 40 degrees right here. Now, in order to find the angle right here, we can use some algebra. So we know that the angles inside of a triangle must all equal 180 degrees, meaning that 40 plus 30 plus this angle equals 180 degrees. Now, if we do some math, we could see that 180 minus 30 plus 40 equals 110, right? So we could say that, okay, this angle right here must equal 110, simply due to the fact that the angles inside of a triangle equal 180. And we found out that these two angles equal 30, 40. 30 plus 40 equals 70. 70 plus 110 equals 180. This whole thing right here equals 180 degrees. Now, we could use the concept of how angles on a vertical line, or on a straight line, sorry, on a straight line must equal 180 degrees, meaning that this 110 plus this must equal 180. We could see that 110 plus 70 equals 180. Now, we can in order to find out the rest of the angles, we can use a combination of our vertical angle theorem. So we could see that, okay, 70, 70, vertical angle, 110, 110, vertical angle theorem right there. Okay, how to solve out these angles? We could see that, okay, this angle right here, 110, is alternately interior to this angle right here, which equals 110, because of our alternate interior angle theorem, which states that alternate interior angles must be equivalent. Similarly, we could see that 70 and 70 right here must be equivalent due to them being alternate angles. And finally, we could top it off by using our vertical angle theorem, stating that, okay, this must equal 70 due to these two being the same. This must be 110 due to these two being the same. So that's a little bit more of a complicated example, something you may see on the ACT, or a concept that, like a variation of this concept that may appear on the ACT, where we see two transversal C and D crossing through a set of parallel lines, but we're able to use our ideas earlier, all the concepts that we went over, to find every single angle within this diagram.